For those who don't know me, I'm Leonidaki. I'm a postdoc fellow at the Institute of Astrophysics in Forth here in Crete. And today I'm going to talk about a project that me and my collaborators are working the last few months, and it has to do with the investigation of the evolutionary path of supernova remnants through their multi-wavelength emission. Hopefully this paper will be submitted by the end of this month. Just a brief introduction in order to shed light on the motivation that we had in order to do this project. In theory, the basic evolutionary model that has been developed for SNRS was done in the early 70s by Walter, and it consists of 4 phases. The first phase, the pre-expansion phase, when it starts when the supernova explodes, and then you have the ejecta that is moving into the interstellar medium with supersonic velocities of thousands of kilometers per second. And this creates a shock, a blast wave, a shock. And during the time, this shock sweeps up mass. And when the mass and a shell behind the shock front is created, and when then the mass, the swept up mass becomes equal with the mass of the initial ejecta, then this phase stops and lasts around 1,000 years, and the SNR enters the second phase, the adiabatic phase, where there you see the reverse shock forms, and it's moving towards inwards the SNR, the center of the SNR. The shock decelerates, and then this phase lasts for around 10 to the 4 years. And then the SNR enters the third phase, the radiative phase, for another 10 to 5 years until it finally fades away. As you can see, if you pay more attention at the pictures and you pay attention on the temperatures, you can see that the temperature at the first 2 phases lies beyond the 10 to the 6/7 Kelvin. So this is the ideal temperature for X-rays to dominate. So the first 2 phases for newly formed SNRs are dominated by X-rays, and the mechanism is either thermal bremsstrahlung, or North-thermal from relativistic electrons. And then if you see the temperature at the third, the radiative phase, the material has cooled off down to temperature 10 to the 5. So this is the right time for the region behind the shock front to cool and radiate in the optical. And of course, the radio, you can see radio emission whenever, wherever throughout the life of the remnant. I think the only thing that the SNR needs to emit in radio wavelengths is a magnetic field. So from all the aforementioned, someone can definitely tell that based on this scenario, based on this evolutionary model, each wavelength Can you hear me?
Yeah.
Now, yes. Now, yes.
Okay. Let me share the screen again. Okay, so yeah, different wavelengths depict different evolutionary stages in the life of remnants. And based on this model, we always talk about a uniform medium. But in real life, things are more complex, meaning that the environment that the SNR is called to evolve plays a crucial role. And sometimes it holds the evolutionary phases of an SNR. And when we talk about the environment, we talk about either the circumstellar or the interstellar medium. The circumstellar medium usually the progenitor star is the one that actually transforms and modifies the circumstellar medium, and the more massive the progenitor is, the more effect it has on the properties around the SNR. What does this mean? It means that a massive star progenitor, and when we say massive, we mean with solar masses larger than 20 or 25, expel stellar winds, and they create wind-blown bubbles, and the cavity that they create around the progenitor and the first phases of the SNR is very, very responsible for the circumstellar medium. And at some points, and in some cases, as it's well inferred from Alexandros and Arkadas in 2007, can speed up or even skip stages in the life of remnants. And a good example regarding how the circumstellar medium affects the supernova remnant is Xray, which is well known to everyone. With the age of almost more than 300 years, someone could tell that based on the evolutionary model and the multi-wavelength emission, someone would tell that, okay, we expect to see radio, as it has radio, very strong radio emission, it has X-ray emission, but someone wouldn't expect to see optical emission. And on the contrary, you see bright emission of forbidden lines. And what about the interstellar medium? When we say that the environment is crucial, the environment as an interstellar medium, we're talking about interaction of the SNR with either molecular clouds, H2 complexes, clumps, or even planetary nebulae. And a very good example is, for this case, is IC443, where you can see the optical emission, it has the radio and the X-ray emission, and usually, and especially the SNRs that are interacting with molecular clouds are in the are categorized as mixed morphology SNRs, the thermal composite SNRs, like IC443, like VRO, and I assume that Alexandros will give us more info about these amazing types of supernova remnants. And we should also not forget and always take into account the selection effects that can dramatically change or hamper the detection of SNRs. So we're talking about when we have low resolution surveys, that means that low surface brightness or more mature SNRs can be missed. Or on the other hand, when we have lack of multi-wavelength observations, for example, people have been afraid of, let's say, observed in the radio at high galactic latitudes because they think, and actually this is the case, but since most galactic supernova remnants lie in the galactic plane, people are afraid of not detecting anything, but many radio SNRs have been detected in high galactic latitudes. And on the other hand, for example, in the optical window, only 25% of, yes, actually it's only the 25% of the opticals, and that's why that's because people were afraid of observing galactic SNRs in the plane of the Milky Way because of the extinction. But this is not the case, and I'm talking from personal experience. So a very good example of a low resolution survey is the Hoenga SNR, which can be seen here. This beautiful nebula, which lies near Vela. SNR. Hoenga actually is a middle-aged and large SNR, but it was first detected in the X-rays with Rosita a few months ago. And this is because although radio data were there waiting for someone to detect them and to use them, because of ROSA that showed nothing, people thought that Hoenga didn't emit in the X-ray, so they didn't pay attention. So from all the affirmation, I believe that you can see the motivation that came in front of our eyes, and that was to investigate the SNR evolution through their multi-wavelength emission. Based on their age and their environment. And apart from that, it was a very good opportunity to provide for the first time, it hasn't been done before, to provide an observational framework for understanding the evolution of these objects. So what would someone need in order for this emission to be accomplished? First of all, we need a large sample in order to have an adequate number of objects and to do our statistics, but it would be better, much better, these objects to have the proximity in order to be studied in great detail, to study their morphology or their physical properties in small scales and in great detail. And the ideal sample for that, as I mentioned before, is our galaxy with a total number of 300 objects. As being stated by the most updated catalog of supernova remnants green in green 2019. And apart from that, we needed to ensure that we will have all the multi-wavelength data needed in order to perform this kind of project, and that is radio, X-rays, and optical. Radio is easy to find because all the SNR community, when they're trying to detect an SNR, the first band they are looking at is the radio. X-rays, we have we are happy that the last years we have a very comprehensive and very well updated catalog of high energy SNRs from Safi Harb that give many info about all galactic SNRs in compilation with the ones that are in Green's catalog. And apart from photos, fluxes, and etc., they also provide the ages, which is very important for this project. And the challenge was confronted with the optical observations were performed with the 1.3 meter telescope at Skianakas Observatory, which was actually a great. It was very lucky for us to have an entire telescope in our disposal. So, in order to have a sample as a first step, we didn't start with observing all 300 SNRs, but we started with the X-ray emitting ones. So we searched at Green's catalog and at Safi Harb's high energy SNR catalog, every SNR that has been observed and detected in the X-rays with any satellite, either this is Chandra, Rosat, Aska. And we found that from the 300 objects, 150 in total are X-ray emitting, with 90 of them being in the northern hemisphere and 60 in the southern. So we focus on the northern part. We don't put any constraint on the morphology or the type yet. The only constraint we put at the moment is the size, because 10 minutes per second is the field of view of the telescope. So in order not to perform mosaicing and just have a single frame, we ended up with the final sample of 29 SNR. So the last years we started observing these almost 30 SNRs in 4 filters: H alpha, sulfur 2, oxygen, and H beta, with typical exposures of at least 1 hour per each filter. And the reason for choosing this filter was not random. Apart from the Balmer lines, the forbidden lines were chosen because these lines are indicators of shock excitation, which is the case in SNRs. And as standalone filters or in combination, they are indicators for great parameters in SNRs. For example, the sulfur 2 to H alpha ratio is the empirical ratio to detect SNRs, or the oxygen line. This oxygen line is an indicator of velocity. Here I list all the 29 objects for which we have images in the radio and in the X-ray bands. And let me go to my results. So after almost 2.5 years of observing,
excuse me, Anna, you have 2 more minutes. 2 more minutes.
Thank you. Yes. So only 5 out of the 29 were observed in the optical. And it happened that 5 of those are the historical supernovae that we already know. And that is, let's see, you see HelAS, you see Crab, and there were other 2 slides. Okay, it was Tycho, it was Kepler, and another one. Although this actually is in agreement with the basic model of the evolutionary model of SNRs, and we kind of expected that, we needed to see or investigate those 5 objects that gave us optical emission. And that was HelAS, Kepler, Tycho, Crab, and G130.7. And we were wondering if something is in common in order for those objects to give optical emission. In the case of Crab and G130, they are in the category of pulsar wind nebulae, well known as clarions. And since their emission, the mechanism of emission is different from type 1A supernova remnants or collapse, we will leave it for the moment because the emission comes from the wind of the pulse of the relativistic particles. So let's go to HelAS, for example. HelAS, it's known the progenitor to be type 1b star with the original. It's a Wolf-Rayet star with the original mass 20 to 25 solar masses, which actually ended up to only 3 or 4 solar masses when it exploded. And it was found that in order to have this kind of extensive mass loss, it cannot be done with one single star. So the existence of a binary companion is needed. On the other hand, Kepler and Tycho belong to the category of type 1A supernova remnants. And as it is very well illustrated by Alexandros in his publications in 2012 and 13 regarding Tycho and Kepler, and based on the simulations that he performed in order to match the observation with his models, he found that in order to have this kind of morphology and emission, you need an extensive mass outflow from the progenitor binary. So in both cases, for HelAS and type 1A SNRs, you have relatively dense stellar winds with low velocities, and those create wind-driven bubbles, and the cavity that the SNRs are called to evolve inside make them transform the circumstellar medium, and make them create earlier the reverse shock than it was supposed to be based on their age. Okay, so we left here. So these 5 objects probably give optical emission because, let me put it in another way, probably, although we don't expect young SNRs to emit in the optical, maybe cases with single stars or binary systems with progenitor stars to have masses larger than 20 or 25 solar masses may produce optical emission because the reverse shock is formed earlier than it is expected, giving optical emission. And me give you the last result for now. We tried to correlate the age of the SNRs with the X-ray luminosity. So since we have estimated ages for almost all of our X-ray emitted samples, 22 out of 29, from Safi Harb's high-energy SNR catalog, we found that all 22 SNRs have ages below 8,000 years old, which means that they are actually at the first phase, at the pre-expansion phase. And if someone could see the numbers, the younger the remnant is, the brighter it is in the X-ray. And just for an example, I put the 5 SNRs that have been observed in the optical with their age, and you can see that the younger one has the higher LX luminosity, and going down to more mature SNRs, the X-ray luminosity decreases incredibly. And this is not the first time that something like this, someone sees something like this, because the first direct evidence that multi-wavelength emission correlates with evolutionary stages came from Agi et al. 2016, when he performed a very comprehensive study of the SNR population in the LMCs. With 60 objects. And as you can see here, you have the X-ray emission and the optical emission for each pair of objects. And you can see that the X-ray emission is fading away as the SNRs evolve, while the opposite happens with the optical emission. And since I don't want to stress you anymore, I leave you with my conclusions, and thank you.
Thank you, Joanna. Thank you very much.
I'm sorry, guys,
are there any... Okay. Are there any questions? I guess you can raise your hand. Alexandre?
Yeah, thank you. Yeah. Yeah, it was a very, very interesting talk and very informative, depending from the gaps. It's very interesting, this multi-wavelength approach. I'm a bit surprised by 2 facts. The one is that you found the optical emission only in young supernova remnants, which the theory predicts the opposite, that they should not be optically bright and not too involved. So that means mainly due to the interaction, I guess, with circumstellar structures. And exactly. the second one is the direct correlation with the age and the X-ray luminosity. So of course we do expect that gradually the shock wave velocity will drop, so the X-ray luminosity also will start to fade out. But it seems to be dependent from the environment. For example, CAS-A is expected to be evolved in a way more dense medium than Kepler or Tycho. So how do you comment on that? It seems that the age is the dominant parameter than the ambient medium.
Mm-hmm. Okay, if I understood correctly your question, you asked me that although you have a very young SNR with a circumstellar medium that is very dense, how come you see that high, that increased X-ray luminosity?
So it's actually that, as you said, that your result, that the X-ray luminosity seems to be strongly bounded to the age of the remnant, and that seems to be the dominant parameter of the X-ray luminosity and not the ambient medium.
Well, actually, it's both, because, for example, if you have a double emission from an object, let's say either optical and X-rays simultaneously, this doesn't mean that this emission comes from the same region. Okay.
Yeah.
Yeah, actually, you don't expect to see X-ray emission from the same area let's say, where the optical emission comes. So you need a denser environment to have the optical emission and a less dense environment to have the X-ray emission. But based on the facts and the way the SNR evolves, it's more than expected to have a less dense, areas, more less dense areas in the early stages of an SNR than, for example, when they are more mature and they are about to fade away. And this is why the optical emission dominates. And it's not very easy to find X-ray emission unless it interacts with something.
Yeah, thank you.
So we have another question from Manos Zapartas.
Yes, thanks for this talk. So my question / comment is specifically about HelAS. So, so for HelAS, I think from light echoes, we know that it's probably a type 2b supernova. So supernova that we expect, so the progenitor, we expect it to have a thin hydrogen-rich envelope on top. And for type 2b supernova, usually a binary scenario is invoked because it needs a little bit of fine-tuning for a star to be, if it's alone, to be able to strip itself only through winds, exactly at the case of having a thin hydrogen-rich envelope. It will either has a big one or none at all. So it needs a little bit fine-tuning without binarity. However, specifically for HelAS, there were efforts to try to find a companion in the supernova remnant, so it was not there. So although in general for type 2b, we think binarity plays a role, for this specific one, we don't know how it got stripped. And my question is pretty much if these comments that I just mentioned would change any of your conclusions or the way to see these supernova remnants. The specific supernova remnant.
I mean, the comments that you nicely put are the ones that I don't know if there was a gap in my talk when I mentioned those. Did you hear when I was talking about HelAS? Can you see my slide?
Yes. So for example, here I saw a type 1b, and I think for the light echoes, it's a type 2b.
This should be 2b. Sorry.
Yeah. So this is just the things I was saying. Like maybe that we don't really know if it's a binary or not, or if this would change anything. That would be pretty much.
To be honest,
maybe it's not so important. Maybe these differences are small from your point of view.
Yeah, to be honest, I'm not. I don't have expertise on HelAS. I mean, many people have because it's the most well-studied SNR in the universe. But since I was trying to figure out what is happening, and HelAS gives so intense optical emission, I found in the literature from those, for example, those 3 people that they claim that there might be a binary system in order to give this extensive mass outflow.
Yeah, that's the case. It's just that the companion is not found there, so pretty much it's a question mark. That's what I'm saying.
Yeah. But of course, at least as far as I'm concerned, and this project is concerned, 5 objects emitting in the optical is not enough. But still, we can see something from it. I mean, young SNRs emitting in the optical.
Thanks.